Fabulous. Right. So our next presentation is going to be from Stephen Batifol, who, if you've seen his profile picture on the website, you may be slightly scared of. I'm sure he's lovely. He's going to be talking about exploring vector search at scale. And Stephen is a developer advocate at Zilliz, and he's worked as an ML engineer at Wolt and a data scientist at Brevo. And he's a founding member of the MLOps community in Berlin. There's a group, they do meetups, things like this.
Meetups, hackathons, workshops.
Workshops and all kinds of lovely machine learning things. And as previously mentioned, he enjoys boxing and surfing. And maybe not at the same time.
I'm trying, but
you're trying.
Surfing is hard enough already.
Okay, so please put your hands together for Stephen.
Thank you very much. Thank you very much for the introduction. Yeah, just to bounce back on what you just said. So I run the MLOps community chapter in Berlin. And to bounce back to the talk of before, we're doing an event with Girls in Tech Akaravia now, end of November. So if you know some people that would be interested in joining the workshop, either you can come to me, or you can come to Atita directly as well. She's also part of it. So yes, also second thing, I'm not a woman, but I've never been as stressed as I am today as giving a talk, because I've been in the search industry for 7 months. And before that, I was in the MLOps industry for years. So yes, but that's enough about me. I'm going to start with a bit of a story. We're going to go on a bit of a journey. Hopefully you can relate to the first talk that we had today, which is very funnily relate a lot to what I'm going to talk today about. So my slides want to change. Maybe. Maybe not. Maybe not. My slides don't change, that's fine. It's a bit annoying, you know, but I can just improve. And let's go. Nope. We're going to try again. It's the part of the demo effect, you know. Fun fact, I also have a live demo after. So I hope it will work. Perfect, it works. So imagine you are an AI developer, kind of. You start, you know, the happy beginnings. You're like working on your laptop, everything works. You're like, you know, you have this genius idea of doing an AI product. Maybe you're going to apply to IC, you know, as we've seen in the past couple of days, you just need to fork a repo and then you get funding. So you use your favorite tech stack of 2024, Cursor and Claude, you know. You don't need really to write code. You're just going to ask for them to write the code for you directly. You have your app, you're pretty happy, and then everything's beautiful. You have some unstructured data, that's not a problem. We spammed you, vector databases, we spammed you in 2023, 2024 for how to use a vector database. So hopefully you have an idea, and then, you know, you're going to use Docker, you're going to pull any vector database, and then you're going to use it. You start it, you're going to use some embedding models, and then you're going to store your vectors directly. You're happy, everything works well. You get some tractions for your app, and then, yes. But then, you know, you have more and more data coming. You start to have some pains, you know, some growing pains as well. Maybe if you're even fancy, you're going to use some multimodal data. So, you know, what used to take, I don't know, less than 10 milliseconds for your search, is now taking 500 milliseconds, you know, even longer as well. Your index, which used to be, you know, updated very, very quickly, now it's going to take, you know, like some hours. You know, instead of like doing it live, you're doing it at night, and every morning you pray that it actually worked. If you do it daily, you might do it weekly, but then, you know, your users are going to be annoyed, your frustration rises, you know, your product, which used to be so cool, your AI product, you know, then now like the search quality is not good enough. So we're going to start again. Basically, now you're going to start with a blank canvas. You know, you learned that maybe just adding data to a vector database won't work to like a crazy scale. So how are you going to solve that, you know? First, let's have a look at, you know, the data, the different type of index. I won't explain the indexes directly because most of you are very likely more familiar than me about all the indexes. But let's say that, you know, you have hash-based and tree-based. You won't use those. Those are not really useful in our use case. But then you have two most important ones, which are the graph-based and inverted files. You know, HNSW that you probably heard, I don't know, about 1,000 times last year. And then you have Vimana, which is disk ANN. is the fancy name. But then also, you know, you're going to look at inverted file, and maybe you're going to go for those. Then you have an idea of, you know, which index work, how they work a bit more, but then you kind of want to balance, you know, like the speed and accuracy for your search. So you have a look at compression. You know, like, are you going to go for flat, or are you going to go for something that is quantized? You know, you have like different algorithms, because, you know, you're, oh yeah, actually I want a lot of data. I have a lot of data, but, you know, like if you search it, and if you don't quantize it, maybe sometimes it's going to be slow. So then you just, you know, have a look, think about, you know, which one you to go for. And the journey continues. Continue, you know, like now you have a better idea of what like the index, you know, you don't think like, you know, as naively as before, where you would just go for like the default one. Then, you know, like, so back then, the software engineer, and, you know, we always said that, you know, if you go distributed, you have more problems than you actually solve. So I'm actually going to decide to go distributed because I like to suffer a bit. But basically, you're going to have a dilemma now. So you've optimized your index, so you're happy. You've chosen the right data structure, so you're also quite happy. And then you've also, like, you know, had a look at like different compression techniques. So you have a better idea of what's happening. But you still have the problem, you know, like more data in one instance is just like not enough. So it's like, how do you do that then? How do you solve that? So yeah, we go distributed. And if you remember, like the talk of this morning, basically, that's kind of what they did, you know. Then there was also a mention of sharding. So are you going to do sharding? Are you going to go divide and conquer? So you're like, you know, you're going to brainstorm some different ideas. And maybe you go random sharding, you know, like then, you know, like it's very simple, but then you have uneven distribution. Maybe hash-based sharding, you know, more even distribution, but then might be tricky with updates. And then semantic sharding, you know, you might group some similar vectors together, and then maybe you're going to be happy with that. But, you know, it's not only that. Then you're also thinking, oh, you look at your data, and maybe, I don't know, you're indexing, you want to do it for fun, you're indexing Wikipedia because you've seen an article, you know, it's like, I don't know, it's like 350 millions, if I remember coherent numbers. And you realize that, you know, maybe you can partition per language. So you look at your data and you're like, ah, actually, that's pretty good. So sketch out a plan. So you have the data that is coming, you know, you route it to like appropriate partitions. Then you can query, there are queries first, you know, to determine the relevant languages. And then the search is executed only on the relevant partition. So you don't do it everywhere and you like save a lot of time. So that way, yeah, you reduce the search space. So then you have faster results. And then, you know, you're pretty happy. You have sharding, you have partitioning. But then what about, you know, your reading as well? So you're going to scale horizontally. You're going to have replicas. You have, you know, you have each shard of multiple replicas. And then the read requests are also load balanced. And the write operations are also synchronized. And, you know, that way you're like, yeah, no, I can read lots of data, you know, at the same time, everything's happy. There is another problem, which is this one, which is the cap theorem, that you are likely very familiar with. But, you know, you can't have consistency, availability, and partition tolerance at the same time. So then you have a look, you decide which one to go for. You read on the internet that, you know, you can't have all of them. But then, wait, it's not over. What about real time now? You know, your users, now we want it now. We always want, I'm addicted to like real time things. So I really hate waiting. So then, yeah, I want it now if I have your cool product. So then you maybe gonna use like write ahead logs, maybe some two-tier systems, you know, maybe like the fresh data is stored somewhere and then your historical data is stored somewhere else. What about the index? You know, I'm gonna build an incremental indexing. So those are like the things you have to think about if you want to go real time. And monitoring, you know, like back in my old days, not that old, but, you know, back in the past, I work in the MLOps world, and data scientists usually love to put models in production, never think about monitoring. So yeah, keep that in mind as well in that case. So, you know, like check the query latency, the index update times, resource utilizations, and different things. Then maybe you implement some automated processes, you know, to rebalance your shards. You add or you remove replicas, and maybe you want to perform running updates, you know. Then you're going to have a look. Do you want to host it somewhere or not? You know, like maybe you're going to go on cloud, or maybe you continue on your own infra. So yeah, it's basically a never-ending journey. I think from what I gathered from the talk this morning, it can secure you a job at Delivery Hero if you want to redo everything, basically. But maybe you don't want that because, you know, like you always have to basically keep up with what's happening. Like, you know, like maybe there's a new index algorithm that is coming. Maybe you have some optimization for like GPU, vector search, or some CPU-specific ones, and different things like that. So yeah, if you did that, congratulations, you just built Milvus. That's basically what we do. And yeah, that's what I'm going to talk about now. That's the architecture we have. No worries, I won't bore you with like too much details. But that's a fully distributed architecture. So we have, you know, as I said during the talk, we have a load balancer, we're happy. Then we balance that. We have like different services running. So the coordinator services are here. They're just here to tell you where to go, basically. Then we have log brokers. So it's either Kafka or Pulsar. So, you know, we have access as well to the real-time data. Then we have some nodes which are in the Kubernetes world, which are basically pods. Those ones are very stupid. You know, they just get some data from point A to point B, and then we store everything in S3. So that's very similar to what I heard this morning. So very good job on this one. We're going on the same route, so that's cool. But yes, that's basically it. And I'm going to touch more about how we actually can do it like at billion scale. And the way we do it, so we use MinIO to like store vectors and indexes. So everything, you know, is like fully stateless for us. Then we have Kafka and Pulsar for, you know, data insertion and real-time data updates. Then, you know, like the usual Prometheus and Grafana. And then we have CRDs directly as well when I run it directly on Kubernetes. And a bit more into the details. So we have shards by default. So like we can boost like, you know, the ingestion rate. And then in Milvus, we have what is called a segment, which is a single unit of data. And a segment is smaller than a partition, which is smaller than a connection. And when you push some data, what we have two kinds of segments. So we have the growing segment, which is the one, you know, handling real-time updates. And on this one, we just build a brute force index. So you can query it directly. And then we have seal segments, which are the ones that are immutable, you know, and then on this one, you build an index, and then you do the search. So again, very similar to what they built this morning. So I'm pretty sure they're on the right road here. So yes, fully distributed architecture. Basically, some nodes to go into it. So the query node is only here, you know, subscribe to the log broker for real-time querying. And it's also the one that is converting new data into the growing segment. So, you know, the real-time data that you have, that's what allows you to then query it directly. Then it also has access to the seal segments. So those ones are the old one. They're like on the object storage, and that's where you build the index on top of. Also allows you to do like hybrid search if you fancy that. The other one, data node, you know, it's subscribed to the log broker again, but this one is here to handle like updates and deletions and different things like that. This one, the index node, you know, the name isn't like quite clear what it does. It builds the index, hence the name. And then this one, you can like always like, you know, you can put it in a serverless way, basically. So you can only like scale it up if you're actually going to need to build an index. And, you know, it's what I was saying. You don't want to build like the whole index all the time. So how we do it, and if you're going to do it yourself, how I recommend doing it is like you divide your data. And for us, it's divided into segments. And then we build the index directly on top of those segments. So we don't have to rebuild the index all the time because otherwise it would take ages. Then for the search, we do it in a distributed way. So, you know, you have your different query nodes. And then each query node is doing the search directly. So then you have parallel processing. Then we give each of them give the result back, and then a proxy is the one, you know, like giving you the result to the user. So then combining the results back, and then give you actually the good results. And that's enough yapping. So I've decided that I was going to do a demo. So if you've seen me yesterday on my laptop, it was because I built the demo. I talked about search at scale. If you've seen me in like different meetups and stuff, you know that I usually always do demos. So I'm gonna go, and the Wi-Fi here is not fabulous, so hopefully it works. But I'm just gonna explain, you know, like at the same time, hopefully I can connect to my cluster. Yes. So I'm just connecting to my cluster. for full transparency, I'm obviously not running that on my laptop because I'll show you how many vectors I have. But I have 483 million vectors. So, it's not a crazy amount, but it's a good amount. And I can clearly not store that on my laptop. So yeah, I put it on our cloud offering. I'm not here to talk about that, so no worries. But I connect to basically Milvus that is hosted in the cloud. So I have my index. So it's, it's built on the 483 million vectors. The type, as you see here, is an auto index. And just to explain a bit more, what we mean by that is that it's basically our own version of HNSW if you go for like performance optimized, or DiskKNN as well. If you want to go, if you want to be save a bit of money, and then you don't care if you're like a bit slower. Then we also have support for DiskKNN. The good part is that we have some fancy ML for query parameter recommendation. So, you don't have to think about the hyperparameters that you may have for HNSW or DiskKNN, we take care of that for you. The data set, so it's a subset of Lion 5B, which for the people that are not familiar, it's an open source multimodal data set. And yes, we load 500 million vectors from it. And it's basically like Clip. So, if you're familiar with Clip, it's like image text pairs, basically. And we have it directly in our cluster, so I don't need to build it again or anything. But I'm just going to show you. So I'm only going to take a sub part of it because again, the whole data set is gigantic. So I'm going to load it on my laptop. I should actually have it already, otherwise it's going to take a while. But I'm just going to go for the first one. And what I want to show you here, I'm not going to show you the recall because I actually have no idea of the data set that I'm using. But I can just show you QPS, how many query per second can we have on something that is running 500 million vectors, approximately, and that is running HNSW for us. So I'm reading the Parquet file. There's only an ID and embeddings. There's not much else. So I can show you the embeddings if you want. And then, yeah, we have that. We have our embeddings. I have my data sets. I just built a function to actually benchmark the maximum QPS that I could have. So I'm going to do my search. And then for my search, then I'm giving a batch of data. And this batch, I'm just going to try if I should give 100 data at the same time, 100 embeddings, 500, 1000. And then I'm just going to play with that. And basically, we're going to see how much QPS we can have, given that we have, around 500 million vectors. So I'm just going to run that. Well, that's the definition of the function. And then, it's what I said. This one, we check, I'm going to run with 100 vectors, 500, 1000. And then here is what I said before, it's the different parameters list, but we abstract that away from you. So you can just have a look now and see. And yeah, basically I'm running it. So we're doing it for we've done it already for 100 vectors, for 500, it's done. And for 1000. Hopefully it should be fairly fast. Otherwise my demo is broken, but it should be good. And here, it's just a vector search. There's nothing else. I could do some filtering if I wanted to, very similar to what we've seen before. But just because my talk is vector search at scale, I only do that. So we can see those are some, I didn't optimize for anything, but if we go for 500 vectors, if we're here, and some search parameters, then, we can play with them, but we can see what's my highest here. My highest is 238 QPS per second. So we have 238 query per second running on our connection, which is 500 million vectors. So it's not too shady. Likely, if we were to run DiskKNN, would obviously have fewer QPS, and then it would the latency would be higher. I'm just going to show you quickly. Actually, I have to do that. I'm going to show you quickly as well the latency, if the Wi-Fi is working. But the latency should be about less than 50 milliseconds from what I checked yesterday when you've seen me on my laptop there when I was building my demo. So no, it's here. Yeah, so the average is 45 milliseconds. The P99 is 97, sorry. The P99 is 97, so about 100. The average was about 45 milliseconds. So that was like, just an idea of how you can like then do search at scale, but not done. Have more yapping to do. So there's also like a thing that I actually like, like Joe yesterday talked about Copali. He really loves it. There's something that I really love, which is something that is made by NVIDIA. So you have, the usual nearest neighbors. You have the different indexes, like brute force, IVF, whatever. You have one that is called Kagra. Who's familiar with Kagra? Not surprised. So Kagra, it's an algorithm developed by NVIDIA. So it's basically HNSW, but on GPUs. So it's HNSW on steroids. And it's going to like parallelize your queries as well, even for like individual queries. So then, it allows you to have like a higher throughput and lower latency as well. Obviously, GPUs are more expensive than CPUs. So then, you might not always use it. But just going to show you a quick benchmark so you can have an idea of, what's going to happen and like the performance that it has. So we have like these benchmarking setups, So it's running on AWS, and then we have two GPUs, two instance types that are running GPUs, and one that is running a CPU. So just for disclaimer, I'm only trying on Milvus, like there's no comparison with the others. It was just like to show you just the impact of adding GPU search, it's not towards like the other vector database, but you can see with only a search batch size of 1, your HNSW on CPU is about 600 queries per second. If you add IVF flat, on GPUs, you're about 1,000. You're already happy, but it's not mind-blowing, If you go Kagra, which is the NVIDIA one, if you go on T4, then you are about 4,000 queries per second. If you go on the A10, then you are about 5,300 queries per second. So you can see like already the improvement, like it's really a good improvement. But also remember, GPUs are really good at like batch. They're not very good at, like individual queries. Just bigger batch. So yeah, like your HNSW is about 650. T4, you're at 12,000 here. And then if you go on A10, you're at about 20,000 queries per second. If the same for, batch size higher, I won't recite the numbers, but you can see GPUs really like when you have a batch size that is quite big. So then with this one, you're about 32,000 queries per second. Whereas on CPU, you are like, I'm going to be kind, I'm going to say 700 queries per second. And then also what's cool is that for the index building, it's also way faster. So even though, yes, it's more expensive, in the end, because it's way faster, you can also then stop, like your node running the index. So for CPUs, about 500 milliseconds. And then on GPUs, you're about a minute or even less. And then what's fun is that so they have a whole paper where they tried to scale their indexing using Kagra. And so then they have raw text, which is 1 terabyte of raw text, which is a lot. It takes about 12 hours to ingest the data. They're working on like improving it. And then they just did a tumbling window chunking of like 300, nothing fancy. They don't really care about that. So you have 2.5 terabytes of vectors, but then to build the index, it takes about an hour. If you do it on CPU, it takes about 6 days. So yes, technically GPUs are more expensive, but then, like you would actually then save a lot of time by, like you don't spend 6 days building your index. Also, like maybe your process will crash or something. So yes. And then just so you have an idea, so some benchmarks with recall. HNSW is blue. HNSW is on the left side for the screen. And on the right side, it's everything that is related to Kagra. So, you can see your HNSW, the recall of 0.85. We can say like 3,000-ish requests per second. And Kagra, the highest one, is at more than 10,000. Again, batch size of 1, so it's not where you shine. You increase the batch size, you go to 10, you're about 100 queries per second for Kagra, whereas your HNSW is about 40,000. if you go for the lowest recall. And then, if you want to increase your recall, then you're about 20,000 for HNSW, and you're still at about 80,000 for the for Kagra. But then GPUs love big batteries. So if you go for 10,000, then the query per second, you are actually don't have the numbers, but you're at more than 1 million for Kagra, sorry. Whereas HNSW would be like in around 100,000. So yeah, if you ever do that, you can what I talked about before, but increase the number of data nodes. So then you have like better ingestion performance. Also, you can place the different index and query nodes on different GPUs, sorry. And yeah, increase like the segment size. So then, like the search latency and throughput will also increase. Then it looks like that. So yes, so for now, then your query node is running directly on GPUs, your index node is running on GPUs. And then that's how then you can use Kagra if you want to, and then have like some insane scale. And yeah, now when I talk at scale, what is a scale for us? I think our biggest single Milvus instance is about 10 billion vectors. Our biggest one on Kubernetes is about 100 billion. So that's usually the scale we're talking about. And that's it. I was Stefan Batifol. I work for Milvus. Thank you.
Fantastic. Thank you, Stephen. So, yeah, some big numbers there. So, do we have any questions for Stephen from the floor? You all understood it completely, I guess.
Thank you. Some great numbers. Today I learned that GPUs love batches. But can you give me some, just so I can wrap my head around how you would apply that? Can you give me some use cases or some practical use cases where you see queries coming in those large batches that you can process them so I can understand them?
For us, it's like some really big customers, like you're like think of governments where like I'm working with one and they have petabytes of data, for example. So then it's more in that one. And I think they have, if I remember the numbers, they have like 30 million people living there. And then they're building actually a whole like rack system and a whole organization system, like where everything is on an app. And so then they need, like everyone is using their app to do everything. So like think you're buying a car, then they're actually scanning the app and be like, yeah, I transfer the ownership to that. And then they basically do like a search through like everything that has ever happened with this citizen. So like think every email that's been shared with the government and everything like that. So that's the kind of use case. Obviously, I just wanted to show it because not a lot of people know it, and I thought it was cool. But yeah, that's the kind of use case where it's useful. Not for every day.
Great, thank you. So I think we had a question at the back here.
Hey.
Nasdaq. So question about the search performance from the indexing. I think it's clear that the GPUs outperforms the CPUs, but like on search performance, I didn't get like what is the expected improvement there, like in P99.
Like on this one, for example?
Which one?
Sorry, do you see?
Sorry, maybe in the see that.
So this one, for example, is a benchmark using GPUs, where you have the recall as well on the bottom part.
And this is using IVF, or you also...
No, it's HNSW on the left. It's HNSW, so running on CPUs on the left.
Okay.
Like here. Here you're running on CPUs on the very left one.
Okay.
And then, yes, those two are IVF running with Raft, which is, like the rapid algorithms from NVIDIA. And then Kagra, which is like HNSW on GPU on the right side. So yeah. Here. And here is IVF on GPUs.
Okay. Thank you.
Thank you.
Thanks. And I also noticed you seem to have your own personal collection of sweets on your table. Right? Very impressive, thinking there. Well done. Okay, so we've got a question from our online audience. Andy Hind. Hi, Andy. I may have missed if CPU, GPU have compatible data on S3. Can you mix and match?
What do you mean?
Do you understand the question?
Can you repeat the question?
I may have, Andy, you may have to retype this, but I may have missed if CPU or GPU have compatible data on S3.
But I
Can you mix and match?
guess if you were talking about, sorry, the slides are coming on Zoom. I guess if we're talking about those, so here, like the GPUs are talking directly to the data that's on S3 as well.
Okay.
And then the way we do it is that, so we don't throw everything at the GPU if we don't want to. So if you do like a query, it's like, you know, like, I don't know, you have two embeddings. And then we're going to do a CPU search. And then we usually redirect for GPU for heavy loads.
Okay.
So
I see.
Yes,
So,
that can answer the question.
yeah, I hope that answers your question, Andy. If we've entirely misinterpreted it, please retype it and try again. Any other questions from the floor?
Hello, great talk, thanks. I have a question, like, can I run Milvus on my own infrastructure on premise? And do you provide feasible instructions how to do it? And then, you know, if something is underperforming, can I easily find the documentation, what needs to be scaled, if it's a query node? Okay.
Yes, you can running on premise or wherever on embedded as well. Like we work with ARM at the moment to also like do like very small vector search. So yes, you can. Then there's documentation. You have to tell me if you actually find the answers. I find the answers, but I know it's a lot. So, so yes, you can.
Well, so to find the answers in the documentation, you need some kind of, I don't know, search engine.
I don't know. Yeah, it's something weird like.
Okay, and another question online, Deborah Barter. I observed that at high recall at around 0.95 HNSW on CPU, performance dropped significantly.
Yes.
Why so?
Very good question. I don't know the answer.
Okay.
So I won't go live and be like, try.
Okay. Okay. Well, maybe we'll research that and answer it on Slack.
Yes.
And see if we can find the answer and get back to you on that one. But well done. You get a badge for beating one of our speakers. And Jagvir asks, is this ready to be deployed in the hot path of search, such as on a big e-commerce website?
Yes.
Yeah.
It all depends on the funding you have. No, so yeah, I mean, we have like, GPU search is very niche. So like, you know, for now it's still quite expensive. So mostly wanted to talk about it. I wouldn't recommend it except if you have insane scale, as I talked before, you know, like your government or something. So like for an e-commerce website, try with CPU first. Then if you really struggle, we can go on GPUs, you know, then it's only about rebuilding the index for like to be like GPU ready, and then you can work that way.
Okay, thank you. Okay, any other questions from the floor? Yes, I'm at the back.
Yeah, hi, nice talk. Sorry, I could maybe get this from documentation, but just out of the box, are the nodes in the Milvus, can they have multiple rows? So, or
Multiple what, sorry?
can they have like, are the nodes in Milvus multi-role? So a single node could be an indexer or whatever, or is it always split? So when
No, it's always, I mean,
always...
except if you go standalone, but otherwise it's always split, yeah.
Okay, thank you.
Okay.
That way you can like scale up and like each one of them individually.
Okay, any further questions? Right, please give a round of applause to Steve.
Thank you very much.